All right, welcome. Everyone is preparing for 2 days off. I'm sure you have a mountain of things to get through. So for us, I did have a lot of people reach out and say, hey, can we have an extension for the first presentation? And yeah, I can do that. But I also want to reward anyone who was able to get it in on time. So if you're able to get it in by the original due date, which is tonight, then I will reward you for that. I haven't decided how, but it'll be good. So I will extend it. I'll send out an announcement so that everyone's aware. And today, and another kind of administrative thing that I wanted to mention is that on November 26th, which is a Friday, so it's a ways out, but I guess I should make a note about the extension first, but also November 26th, I'm gonna post a video, so you'll have to just watch that video. There's no in-person class that day. Had something come up and I thought, you know what? I think you guys don't mind having Fridays off. So I thought, well, should be safe. So I'll post the video on the 26th, but the first presentation is supposed to be due tonight. And if you submit on time, I will reward you for that. But I will extend the due date. So the new due date will be, I don't know, people are kind of playing it cool and saying Friday, but I think I'll just say Sunday night, and then you can let it haunt you all weekend. I wanted to have it due on the Wednesday so that you could be free from all of this for your mountain of other work. But I understand that that's not really how it works. But wouldn't that be so nice, right? But I will extend the due date until Sunday night, Sunday the 14th. At 11:59. Okay. Also, quiz 3 is going to be available. Confession time. I don't think anyone was going to just go right into the quiz without kind of brushing up on the notes first, but I am still, there was some typesetting issues that I want to fix because otherwise it reads all funny sometimes. So I just want to go through and make sure that that's all sorted out. And I didn't quite have time to finish that before class, so I'll do that after class. And so it'll be available kind of definitely within 2 hours after class ends. So sometime this evening. So quiz 3 will be open tonight until Sunday as well. Sounds like you're going to be working on my class a little bit this weekend. It will be open until Sunday, November 14th at 11:59. And same thing as always, it's a 50-minute timed quiz. With 20 questions. Okay. Good. Oh yeah, and then note November 26th, which is a Friday, we won't have in-person classes. No in-person class, which means a video will be posted. For you to watch on your own time. Okay. That's just a heads up, so mostly so that I don't forget. And then I think I've scheduled quiz 4, so our last quiz for that December 3rd. It's posted on Moodle, so so I think that should be good. Okay. It was just on Monday, so I kind of want to just jump into it. A lot of the stuff that we covered last day is going to kind of resurface. So let's see here. So I do want to finish chapter 7. I will kind of gloss over some of the things and focus more on some of these things, but I have made sure that pretty much, I mean, besides some of these conceptual things, all the questions on the quiz can be answered just by, you know, reading our class notes or reading the summary notes. So, so there are some things that I can kind of gloss over because I know what's on the quiz, and then there will be some things that I'm going to focus on. Okay. Where did we end up? Okay. We started talking about multiple regression. Now, multiple regression is when we have multiple X values, right? X1, X2, X3, X4. And we said, okay, so if I build a model using these X values, so these independent variables, then we can test to see if a slope is contributing to being able to predict the Y value. Okay. And so we said we can test the hypothesis that a regression parameter beta j is 0, right? If the slope is 0, it means that there's no relationship between that X value and the Y, right? So here, we can test whether an independent variable X subscript j, right, is useful in helping us predict the Y value, is useful in predicting Y, right? So that's our Y hat. Y hat is the predicted value of Y. By testing the hypothesis, and I'm just going to grab this here. How can I extend this? Nope. There. Okay. So it uses a t-test and it uses the estimate, the coefficient, and then we have the standard error of the coefficient, and that gives us a t value. Now we're doing a t-test, which means we would use the t distribution to find the p value. Uh-oh, sounding like chapter 6 all over again here. So here regression output includes all these statistics as well as the p-value, right, for each test, right? Because each slope is going to be tested. Is it significantly different from zero, right? A slope different from zero means that there's something going on. Oh yeah, so I am hitting enable on this live transcript. It's not working though, so I'm gonna hit it now and nothing still. For the past 2 days, or I guess yesterday, it started not working, so I'm really sorry, but I don't know what to do. So the regression output will include the p-value for each coefficient. So what we saw was, okay, if I have some sort of, oh, I skipped ahead to that output. Hey, where's the one that I was using yesterday or last day? Here. Okay, where's this line? Man, I'm Struggle City today. Oh, it's because I've got a page break here. Okay. This got weird. So it gives us the p-value here. We talked about this last day, so I don't feel too weird about it being so small. Maybe I'll crop top it. Crop. How about that? How about them apples? Right. And so what we'll see is we're testing to see if those coefficients are significant, right? Are they contributing to predicting the y value? Right. And so a p-value less than alpha equal to 0.05, right, as a default. Typically we use 0.05. So a p-value less than the alpha level of 0.05 means the coefficient is significantly contributing to being able to predict the value of y. Means the coefficient is significant, right? And so usually we just say it's significant. And what that means is it helps predict y. Often we notice that the intercept is just, it's going to be non-significant a lot of the time. Unless it's a value that can happen, then maybe it'll be significant, but usually we have to have some sort of anchor, right? And so we just let the intercept be non-significant most of the time. Okay, so the intercept is allowed to be non-significant because we need some sort of anchor for our line or our plane or whatever. Because we need an anchor for our line, right? Or some sort of starting point for our predictions, right? If I let the number of miles driven and the number of deliveries both be 0, then my predicted now I'm trying to remember what the example was. Amount of time traveled, I want to say, would be 0.0127 hours, right? Doesn't really make sense because you wouldn't make a delivery if you're not traveling any miles and you're making 0 deliveries, right? So often the intercept doesn't mean anything, so it's not meaningful, but we need it to have kind of a jumping off point. Okay. So that's kind of where we're picking up today. Because we talked about what do we do if we have non-significant independent variables. And that's going to come up later, so I'm going to kind of table that for a little bit. But there are lots of methods that have been developed for, okay, so what if you build a model and it turns out that one of these variables is not contributing, it's not doing anything to help you predict Y, right? And so then what do you do, right? And so we talk about things like backward elimination, stepwise elimination, forward elimination, that kind of thing later on. So I'm going to parking lot that and talk about multicollinearity. So multicollinearity is referring to the correlation between the independent variables. Okay, so we're calling them independent variables because they're independent, they're happening independently of Y, right? But that doesn't mean that they're happening independently of each other, right? So here, multicollinearity is talking about, okay, if there's correlation between your X values, then you need to address that, right? Because then, you know, if you're doing something like, let's see if I can think of something off the top of my head, maybe if you had miles in your, so the miles traveled, yeah, that would work. So what if you had miles in your model as well as how much gas you used, right? So we know that, okay, how much gas you use depends on how many miles you travel, right? And so those would have a really strong correlation. So maybe in order to keep our model as simple as we can, and that's going to be a goal, our ultimate goal is to keep our model as simple as we can and still be able to get good predictions. And so then we could look at eliminating one of those variables, right? Because if we have the miles, then maybe we don't need to incorporate the gas variable because we've already captured that information here, right? And so multicollinearity is talking about the correlation between X variables. Okay. So here, kind of fancier, in multiple regression analysis, multicollinearity refers to the correlation among the independent variables. Okay. And so what happens if you've got two things that kind of are conveying the same information to the model, then you might get something that's not significant because you've got another variable that's kind of carrying that weight when it should be significant, right? And so, and stuff like that, right? And so there's this kind of overlap of information being contributed to the model. Maybe I can make that a little bit smaller here. So here, it's basically saying there could be overlap. And I use the term overlap in the sense that, okay, if they're giving the same information, then I consider that overlap. So there could be overlap in the information put into the model. Okay. So what you would do is, so to check for multicollinearity, then you're going to calculate the regression coefficient, or sorry, the correlation coefficients. I don't know why I said regression. It's all regression, I guess. So you're going to calculate the correlations between each of the variables, right? And so you'd have some sort of correlation matrix, right? And then any correlation that exceeds 0.7, so plus minus 7, 0.7, because correlation goes from -1 to +1, right? And so to check for multicollinearity, calculate the correlation between each possible pair of x's which is usually done in a correlation matrix. Oops. Okay. And any correlation larger than plus minus 7, so and any absolute value of r greater than or equal to 0.7. How about that? Because correlation can be negative, right? But the stronger it gets, the closer to 1 or -1 it is. And so any correlation greater than 0.7 could indicate multicollinearity. Okay. I'm going to skip this, the F test, because it's just an extra note. So, and we talked about it last day. So the F test is basically just, I say I'm going to skip it and then I go into it. But it's basically like, hey, is there anything going on in there? No, okay, then I won't bother. Right. And it's a pretty old school thing that we had to do because all these calculations took time and they were, you know, fairly complicated. And so if we have this kind of simple test that we can do to see if there's anything worth exploring, then that's a good thing. Right now, we don't need it because we can just run whatever model we want. And that's it. Right. But so it's kind of more of an old school thing, but it's worth knowing because for all regression output, it'll run this F test, right? And so what it's testing is if beta 1 is equal to beta 2 is equal to all the betas. And so what it's testing is whether all the betas are equal to 0. So nothing is contributing to predicting Y, right? And then the alternative hypothesis is that at least one of these are helping us predict Y, right? But what I want to talk about now is we've talked about numerical variables, so incorporating numerical variables into our model, right? And so, or quantitative variables, I should say, of X. And we are still assuming that our Y variable is going to be quantitative or numerical, because that's what we're assuming right now. And so, but you might remember logistic regression, or you maybe heard it at some point. But anyway, so we could do that, but here we're talking about categorical independent variables, right? And so what if we want to incorporate a categorical variable into our model, right? So in our example, right, we could have something like, we want to indicate whether a driving assignment included travel on a congested segment of a highway during the afternoon rush hour. Okay, and so what we could develop is we could develop these dummy variables, they're called. So a categorical variable we recode as a dummy variable. Okay, so we will usually, I say usually, but I'm tempted to say always, but as a statistician, we never commit to anything so so concrete. So I'm going to say usually, but what I actually mean is always, right? So we will usually recode all categorical variables into dummy variables. Which 0 is kind of off, and 1 is on. Okay, and so what we can do is a dummy variable is basically this on-off switch. Okay, and so if there was if they didn't have to travel during rush hour, let's just shorthand it as that. So basically this will kind of shorthand this as no rush hour. Oh, that doesn't look like rush, but I think you get the idea. Right? And then the alternative is if we turn the rush hour on, how does that affect the model, right? So you can see how you're able to incorporate things like, okay, well, was it during rush hour or was it just normal traffic, right? And so here, this is the rush hour. Okay. So this dummy variable lets us basically develop two separate models, right? One with the rush hour on and one with the rush hour off. Okay. So the dummy variable, and at first it sounds really offensive when you call it a dummy variable, but it kind of grows on you. It's kind of cute because it's just a little on-off switch, right? So a dummy variable allows us to build basically two separate models, to build two models out of one, right? The first one is with rush hour. I mean, hey. And then the other one is without rush hour. All right, then we can see if the rush hour component doesn't help in predicting the delivery time, then I'm stumped because I think it would help us predict the delivery time, right? But if it doesn't, then we could pull it out of the model and we could look at some other categorical variable, right? But that's the idea with this dummy variable, is it's basically an on-off switch. So what we would get is we could look at this output here. So we get an R squared of 0.8838. And we talked about R squared. The coefficient of determination here is, but usually we just call it R squared. And it's a goodness of fit measure, right? And so how well does this model fit the data? How good is it at predicting future values? And so a high R squared value is what you're going for. And so here we've got an R squared of 88.38%. Okay, so that's high, that's really high. And we're given these coefficients. Okay. And so if we look at these coefficients, right, then we have this intercept, negative 0.33. And if we look at the p-value here, it's just barely significant, right? So it would be significant technically because it's less than 0.05, but we also wouldn't remove it from the model just because it was insignificant before. We have to have some sort of anchor, right? And then looking at all these other p-values times 10 to the negative 105. Imagine moving your decimal 105 places. That's a lot, so no thanks, but we know it's really small, right? So we see that all of these p-values are now significant, right? And so that's the first thing that we want to make a note of here is we see all coefficients are significant. Okay. And so what we can do is we can build this model using these coefficients. Now, I'm just going to inspect kind of briefly here and rounding to, let's say, 3 decimal places. Okay. Oops. Rounding to 3 decimal places, we find the model, we find the estimated model is y hat is negative 0.330 plus 0.067 times, let's say, x1 for now, just generically, plus 0.674 x2 plus 0.998 x3. X1 is the miles. X2 is the number of deliveries. And X3 is the rush hour dummy variable. Rush hour dummy. And then Y hat is the predicted delivery time. Okay. So what we get is if we focus on the dummy variable, right, it can be 0. If I multiply this by 0, then I'm just left with the remainder of the model, right? And so that would be my model when there is no rush hour, right? Or I can turn it on, and then all I'm doing really is I'm adding 0.998 times 1, which is really just adding 0.998 to the predicted delivery time, right? And so that's the difference between having there being rush hour or no rush hour, right? So pretty cool stuff, right? So here, we just talked about this, but I'll bring it in for kind of completeness sake. Uh-oh. I'll keep it on the same page. Kind of small there, but yeah, so here, oh, should have gone to 4 decimal places. Oopsies, to match, but that's okay. I went for 3 and that's fine. Right, so remember from last day, how we interpret these coefficients is that for each unit increase in x1, for example, right, the predicted value of y hat, is going to increase by 0.067, assuming that x2 and x3 are being held steady, right? And so that's how we have to interpret these coefficients, is we can only look at one variable at a time and then assume that the other ones are being held steady. Okay? And so it's all written out here, but let's keep going. So what happens if you don't have a binary variable? So what if you don't have a variable that's naturally 0, 1, right? So what if we have more complex categorical variables? So if a categorical variable has more than 2 levels, okay, then we have to be really careful when we're constructing and interpreting the dummy variables, because what we're going to do is we're going to take each of the levels of a categorical variable, right? So if we think about, let's say, I don't know, hair color, for example, right? Then we have more than 2 categories, right? We could reduce each hair color to either you have brown hair or you do not, right? Either you have blonde hair or you do not, right? Or either you have red hair or you do not, right? So what we're able to do is, even though we have multiple categories, we can reduce each of them to a dummy variable, okay? So what we're going to find is that if we have a categorical variable with k levels, so k generically, k levels, then what we're going to need is we're going to need k minus 1 dummy variables. Because what happens is if all the other ones are on, then the remaining option is going to be when all of them are off, right? And then that is also an option. Okay, so I'll just highlight this here so that you can have it. So for example, here, let's see if it's, oh, it's not, okay. Wait. Slipped up here, okay. So if we have a region variable, maybe there's regions A, B, and C. So now notice that we have 3 levels. Okay. So here we have K equals 3 levels. Therefore, we need 2 dummy variables, right? We need 2 dummy variables. Okay. For example, if we have region A, then x1 is 0 and x2 is 0, right? So if both x1 and x2 are off, then that's an indicator that you're dealing with region A. Okay. If x1 is on, then you're in region B, right? And then of course, x2 has to be off. Okay. And so for region C, then x1 is off and x2 is on. So here, let me just see if I can. Region A is when x1 and x2 are off. is when x1 and x2 are off. So we can build these regression equations, right? And so what we're going to see is that, okay, if we just focus on just these dummy variables, x1 and x2, if both x1 and x2 are 0, then the predicted value of y is the intercept, right? And so that's what makes the intercept the predicted value or the coefficient for region A. So that's the same as the intercept. And maybe I don't know how to show it. Maybe not like that. The intercept is the coefficient for region A is the coefficient for region A. Just like the intercept is kind of this anchor, right? Where does my line start on the y-axis, right? And so if you think about just a straight line, that's the easiest thing to do. Or where does the plane cut through the y-axis? It becomes a little bit kind of hard to visualize that way. So if we just think about a line and we think about the intercept, where does it cross the y-axis? Then now we're saying, okay, well, that's going to be region A. So region A is kind of a jumping off point. Okay. And then, so then if I turn on region B, what happens? So then x1 is 1. So then my predicted value of y is beta or b naught plus b1 times 1. And so my predicted value of y is now going to be region A plus b1. And so b1, the coefficient for region B or x1 is the addition. And I say addition, it could be a subtraction if it's negative, but let's just stick to the positive terms. So it's the addition that happens by adding, by changing from region A to region B. Okay. And so here, oops, it's kind of hard to see with the pink, but I wanted. So here, B0 is the estimated mean sales. So we've been calling it the predicted value of y, but that is the estimated mean sales for region A. And then B1 is the estimated difference between the mean number of units sold in region B and the mean number of units sold in region A, right? So region A is your starting point, and then the coefficients B1 and B2 are going to take the prediction from region A. So region A becomes, so the intercept becomes the starting point. So kind of tricky, but once you've kind of read it a few times and you've kind of wrapped your head around it, it's not so bad. But it is kind of this weird idea that the intercept is now representing a category, right? We can model nonlinear relationships. Wait, sorry, letting it catch up here. Okay. There are some key nonlinear relationships that we're just going to mention. And, you know, if you're working in Excel, then it's really easy to tell it to do these things. I would kind of caution because often a linear regression is going to work. You can often do transformations and things like that where the linear regression is going to work. So, but these are some of the more common nonlinear models that we could have. And it's just nice to have them up our sleeves. So here, first one I want to talk about is the quadratic regression model. And so a quadratic is when we have some variable x1, but we also have x1 squared, right? So notice that they each get a coefficient of their own. Okay, so when you see things that have some sort of curvature here, like this, if you're looking at the shape of your data and you're seeing some sort of curvature, what you could do is you could try modeling it with this quadratic model. Okay. And so if a scatter plot shows you know, some sort of curvature in the relationship, shows some curvature in the relationship, you can try modeling, you can try a quadratic model. Quadratic, that's not how you spell it at all. A quadratic model, right? And so notice here, oops, not that I think it refers to it or anything, but notice that both x1 and x1 squared are included. And maybe what I'll do is I'll change the color of this to dark blue. Highlight the differences. Okay, so if there's some sort of curvature there, then you could try a quadratic model. Okay? There's no harm. Usually when you're trying to model a relationship, you build lots and lots and lots and lots and lots and lots and lots of different models, and then you're comparing them. How do you compare them? With an R² value, typically. Okay. Another model that you could try is what's called a piecewise linear regression model. And there's a picture here. So the piecewise linear regression model, is if you have something that looks kind of like, oops, too fast, too furious. I don't know how it's letting me go off the page right now, but must be some new. I noticed my notability updated. So if you have a relationship where you have you could break it up into two different linear models like this, right? Then you could try a piecewise linear regression model. Now, this point here where it breaks is called the knot. Okay, so here, this is called the knot. So technically, we should predetermine the knot, right? We're based off of knowledge of, you know, prior models and things like that. We should have some knot already decided. But usually what happens is you see data that looks like this and you think, oh, I should probably try a piecewise linear regression. And here it looks like my knot would be somewhere at x = 90, right? Something like that. So, so although theory should determine this value, analysts often use sample data to aid in the identification of the knot. Okay. Okay. But then you basically just go ahead and wait. And build two linear regressions, right? So piecewise linear regression, just as a summary, connects two distinct linear models, right, at some knot. Connects, two distinct linear models at some preferably predetermined knot. All right, not always the case, but ideally. Okay. So you basically have a positive linear regression, and then you have a negative one if you're looking at the relationship that we saw there. Okay. Another common thing that we do is look at interaction terms. Okay. So the interaction terms is the relationship between the dependent variable, so y, and one independent variable is different at various values of a second independent variable, right? And so what that's saying is that maybe x1, right, the relationship between y and x1 depends on the value of x2, right? And so here, what we're saying is that the relationship between y and x1 depends on the value of x2. So then what you should try is introducing this interaction term. And the interaction term is just x1 times x2 multiplied together as if they are their own thing. Okay. So this is the interaction. Yeah. So that means that we're always going to consider how x1 times x2 behaves, as well as x1 and x2 kind of on their own, right? And so it means that we're always going to be incorporating both x1 and x2. Okay. And so we've got this kind of joint relationship between x1 and x2. But so the interaction term is if you think that one of the independent variables, well, that's going to depend on another variable that's also in the model. So then you would include an interaction term if you think that's what's going on. Yeah. All of this it could be in its own course, right? And so, and I think Claude is teaching regression. So of course, all of this should be talked about in more detail, but these are the core concepts that we usually, try our way through. And they'll serve you well, so it's good. Okay. Here, just gonna grab all of this. of course, I've got a page break here. Huh. Maybe I'll do this. So what we said was, okay, if we fit a model, usually we have, usually we have a large number of potential independent variables, right? So sometimes we're going to have so many variables and we're just trying to select which ones might help, right? You don't want to have to go through and look at all the different possible combinations of variables, right? Are you going to have just individual variables? Are you going to have interaction terms? Are you going to have quadratic terms, right? All those things are now options, right? And so you don't want to be able, you don't want to have to look at every single possibility, right? Only x1, x1 and x2, x1 and x2 and the interaction term, x1 and x1 squared and x2, x1 and x1 squared and x2 squared, and so on and so forth. There's so many different combinations. And so there are algorithms that that go through and consider all these possible combinations. Okay. So we don't want to well, first of all, I don't even want to think about all the possible combinations, so we don't want to have to list all the possible model combinations. So we apply variable selection algorithms, right, to help us select a couple of different models. So we apply variable selection algorithms to help us identify model candidates. Oops. Doesn't that sound cute? Okay. There are things like backward elimination, forward selection, stepwise selection, and best subsets. And I'll bring in the kind of the descriptions for those core ones, but the backward elimination is when you start with all your variables in the model, and then what it does is it eliminates one variable at a time, right? So it'll start with the most non-significant variable, and I'm pretty sure it moves it to the back of the list, right? So it makes it the last variable in the model, and then if it's still non-significant, then it's taken out, right? And then it moves on. Okay, what's the next non-significant variable? And then I'm pretty sure it moves it to the bottom. I can't quite remember. Forgot to look into it. I think it moves it to the bottom, and then if it's still non-significant, it's removed from the model, and so on and so forth, until all the variables that are in the model are significant. Okay, what's kind of neat is you could do the same thing starting with nothing, and then identify the most significant variable, add it to the model. Okay, and then I add another one, and then I add another one, and then I add another one, making sure that they all stay significant until I add a variable that's no longer significant in helping me predict y, and then I stop, right? I don't include that one, I stop. What's fun is all these procedures tend to yield slightly different models, right? And so that lets us compare these models. So I'll bring in the descriptions, but you can kind of read it on your own. Let's see here. Oops. How about this? I'll put them side by side. Okay. And so here, for reference, I'll say, oops. Yeah. Okay. So one thing that's going to be a real concern is if your model is too big. Okay, so it has too many variables in there, and you have ended up modeling the sample so well. But what happens is if you have too many variables in there, then it becomes kind of sample dependent. And so we call that overfitting. And it's something that we really want to avoid. We're trying to have the most simple model that could be applied to any data, right? Not just the sample data, because the sample data, we already know everything about the sample. And so what we're trying to do is we're trying to use sample data to learn about what the whole population looks like, right? And so in theory, if we collected a new random sample, then how well would my model do at predicting? So overfitting is a concern. So here, the objective in building a regression model, or really any mathematical model, even though it's cool to have a really complicated model, that's never been the goal, right? Sometimes you need these complicated models, but what you want is you want the simplest, most accurate representation of the population, okay? And so we always try to develop the simplest possible model. Right? And so overfitting is when you've basically, you're describing the sample data so well. You've been able to capture every single nook and cranny of your sample data, right? So imagine you were able to kind of draw a line that captures all that activity, and your R squared is huge and you're so proud of it, but maybe you had to incorporate, 15 different variables. That's not very useful, right? Because then you'd have to measure all those variables in the future, right? If you wanted to use this model. And some of those variables might be expensive, for example, right? So you want to have just a few core variables that you can really leverage for a good model. Okay. And so what we do is we have this cross-validation approach. And so one of the main cross-validation approaches that we use is called the holdout method. Okay, so what happens is we split our sample data into what we call a training set and a validation set. Okay, and so what we do is we build our model on the training set. Okay, so we try to fit our model and we develop a couple of different models. And then what we do is we say, okay, I know the outcome in the validation, in the validation set. So I know these outcomes. So what I can do is I can predict them with the model from the sample. I can predict these outcomes, right? Apply that model to the validation set. And then I can measure how well my model is doing at predicting outcomes in the validation set. Okay, so kind of complicated, but for a really fun example, you can look up the Netflix prize. It was a long time ago now when Netflix was, I think, still sending out DVDs. And so they had this $1 million prize where they released a data set, right? So it was sample data. And the goal, I think, was to predict the ratings of movies. Hey, aren't you guys doing movie reports right now? Right. So what they were doing, they just put it out to the public and they said, hey, if you can beat our algorithm, which means if you're able to predict the ratings better than we can with our algorithm, we'll give you $1 million. And so, of course, it was, talk of the town. And I mean, in the statistics world. And so, everyone wanted to try it and build a model. And someone did manage to build a model. And I think I was reading up on it just before class, and I think it was predicting like 10% better than the Netflix algorithm. So pretty cool. But here, I'll highlight this, kind of a long-winded highlight there, right? And so for a cool example, check out the Netflix prize. It was pretty well known, and I'm sure that there are other companies who did something similar, but Netflix was the big one, and it was a $1 million prize if you were able to predict the ratings of future movies, right? Which helps them determine which ones to put on their roster, right? And so it makes sense. So what they did was they released sample data, and then of course what you would do is you would break it up into two parts. So then you would have a training set, which you would use to build your model, and then to see how good your model is, you would apply your model to the validation set, and then you check against, so did I predict that rating or not, right? And then you'd have a score, and we're not going to go into how you score that, but that's the idea. Okay, so kind of a cool idea for checking your models. Okay. Here comes big data again. And once more, the problem with big data, oops, maybe I'll do this. The problem with big data is that all your coefficients are going to be significant, right? Because you have this huge data set. So your standard error is going to be really, really, really small. And so all your estimates will be significant, right? And so what happens is everything is kind of amplified, right, when you have big data. So multicollinearity, for example, becomes a real problem. And so what you want to do is you want to make sure that your model is good and sound with small data before you apply it to big data, right? Because in big data, all your coefficients are going to be significant. Okay, here? Couldn't find what I wanted to highlight there, but there it is. Okay, so that's the same problem that we keep seeing with big data. Okay, so this is the same problem we saw before with big data, right? Everything becomes significant. Oops. So what we can do is, of course, we would still look at those p-values, but you don't want to build models using just big data, right? You might want to build a model using a smaller set, right? So make sure your training set is small-ish, and then when you apply it to your big data, then it should still do a good job of predicting, right? Seeing if I wanted to do anything there, but I'm running out of time. And the last thing that I wanted to talk about here, hey, it's letting me go off the page and it's weird. Is prediction. So what we're going to be able to do is we're going to be able to build confidence intervals or interval estimates. Like the textbook calls them interval estimates, but confidence intervals. And so we're going to be able to build confidence intervals. We're also going to be able to build prediction intervals. Now, a prediction interval is different in the sense that it's only talking about one value of y, right, for that combination of x. Okay. So we know that the goal of building a regression model is to predict future values, right? And so the goal of regression is to predict y, right? So that's just a good reminder. And so we're going to have some predicted value of y. And what we're going to do is we're going to be able to predict. So what we do is we have some x1 and x2 that we can insert into the model, and then we can get a predicted value at that point or at that combination of x1 and x2. So this is the predicted y at x1 is 105 and x2 is equal to 3. Okay. So what we have, so this becomes our point estimate. Okay. So in addition to that, what we can do is we can have two types of interval estimates associated with this equation. So first we can build a confidence interval, okay, which is an interval estimate of the mean y value given values of the independent variables, so x1 and x2. And a prediction interval is an interval estimate of an individual y value given values of the independent variables. So let me just highlight this here. And what I want to do is I want to underline here of the mean y value, and the prediction interval is of an individual y value. So that's the difference between a confidence interval. A confidence interval or an interval estimate is for the mean, right? So the predicted value of y is the expected value of y, or the predicted or the mean value of y. Whereas the prediction interval is talking about just an individual y value. Okay, so often what we do is we end up building confidence intervals, which is for the mean value, as well as prediction intervals, which is for the individual values of y. Okay. So I've got this example here. Oh, and I'll keep it there because I've got a page break and that's all I wanted to say. But so here, assignment 301, for example, 105 miles and 3 deliveries, we're able to predict the value of, which is the predicted travel time, I think. And then what we can do is we can build a 95% confidence interval. And so they're calling it the half width, but it's really the margin of error. And so 0.193, okay. And then, so that's the confidence interval, which is for the mean value, right? Whereas the prediction interval is for that value of y, right? When x1 is 105 and x2 is 3, okay? Okay. I think that's all I wanted to say, and just in the nick of time too. If you have any questions, let me know, but otherwise quiz 3 will cover up to this point. End of quiz number 3 material. Okay. All right. With that, I'll stop this recording and let me know if you have any questions. Otherwise, have a great long weekend.